In this video, we're going to look at stopping distance, which is the distance which a car travels to fully stop. So when cars stop, they don't stop immediately, they do travel a distance before they stop. Pause the video to do these 5 questions, press play once you've done them. You should have now done these 5 questions. Let's go through them one by one. So the equation which links distance, speed and time. So you might have chosen to write it as speed equals distance divided by time, or you might have written distance equals speed times time. Both of those versions are okay. Find the distance traveled by an object moving at 4 meters per second for 1 minute. So we firstly need to write down our data. So our speed is 4 meters per second, and our time, we can't leave it as 1 minute, we have to change it to 60 seconds. So therefore our distance, which is speed times time, is going to be 4 times 60, which is 240. And what are the units for distance? Say your answer to the video now. You should have said meters. Question 3, how does resultant force affect acceleration? So resultant for so when you get a question like that where it says how does this affect this, the kind of answer that you need to give looks like this. As resultant force increases, acceleration increases. But if you want to get the answer really high quality, you should say resultant force is directly proportional to acceleration. So resultant force is directly proportional to acceleration. So that doesn't just mean that when resultant force increases, acceleration increases. It actually means when resultant force doubles, the acceleration doubles. If the resultant force were to divide by 4, the acceleration would also divide by 4. The equation which links force, distance, and work done, I'm going to do up here. So the equation is work done equals force times distance. And finally, the relationship in graph between A and B here is a directly proportional relationship. And there's 2 ways that we can tell it's directly proportional. What are the 2 things that tell us that this is a directly proportional relationship? So look at the graph. What are the 2 things that you can see on the graph that tell us that it's a directly proportional relationship? Say your answer to the video now. So you should have said it's a straight line and it goes through 0, 0, which we call the origin, which goes through 0, 0, which is the origin. So those are a few ideas which you'll need to understand already to understand the ideas in this video. So let's start by defining stopping distance. Pause the video, have a look at this diagram, press play once you've had a look at it. You should have now had a look at this diagram. So this is actually something which you'll see again if you ever learn how to drive. Stopping distances are very important. There's different stopping distances depending on how fast you're going. So a few things to notice. Firstly, the faster you go, the bigger the stopping distance. And that's why driving fast can be dangerous, because it means it's going to take you longer to stop. But let's just really understand exactly what this stopping distance is. Because if you look at the diagram, you can see there's some distances in blue and there's also some distances in red. So what's the difference between those things? So imagine you're driving a car. So here's a car. Oh, the car's disappeared. So here's a car driving along this direction. And you see a traffic light change. So here's the traffic light, and the traffic light has gone red. So when you see the traffic light go red, firstly, it takes a little bit of time to react to that. So in the time it takes to react, you have something called the thinking distance. So while you're actually reacting, and that can take half a second or so, you're still going to be traveling forwards in the car. So that's called the thinking distance. So that's the distance traveled. That's the distance traveled during your reaction time. So in the time it takes you to actually respond to the traffic light going red, you're not going to immediately put your foot on the brake as soon as the traffic light goes red. The traffic light's going to go red, and then there'll be like a fraction of a second, and then you put your foot on the brake. In that time, that reaction time, your car will travel a certain distance called the thinking distance. And then at this point over here, you press the brakes, then it still takes time for the car to stop. The car does not stop immediately. There'll still be time for the car to stop. That distance there is called the braking distance. So the braking distance is the distance traveled from the moment you press the brake until you stop. So it's the distance traveled from pressing the brakes to stopping. And we call the total of the thinking distance and the braking distance, so we call this whole thing stopping distance. So stopping distance is the sum of the two. So stopping distance is, I'm going to write it out, thinking distance plus braking distance. So to summarize, when something happens on the road and you need to stop, you have your reaction time. That's how long it takes you to actually put your foot on the brake. In that reaction time, you'll travel a distance called the thinking distance. And then once you press the brake, the car will then travel another distance before it stops, which is called the braking distance. And the sum of the two is called stopping distance. Now we're going to look at those individually. So we'll start with thinking distance. So your reaction time is the time it takes you to respond to something. So a classic example of this is if I were to hold a £5 note above your fingers and then drop the £5 note, you'd be very, very, very unlikely to put your fingers together in time to catch the £5 note. People take time to react to things. If you see a traffic light go red, you don't put your foot on the brake instantly. There will be a fraction of a second, usually between about 0.2 seconds to 0.9 seconds, depending on various factors. Usually less than a second. Less than a second, you will have pressed the brakes. But in that time, your car will carry on traveling forwards. And we can actually work out the distance that the car will travel during that reaction time using the formula from before. So before, we had this formula, distance equals speed times time. So we can use that exact same equation, but we can just add the word thinking here to make thinking distance equals speed times reaction time. So it's exactly the same equation as before, except what we're saying is the thinking distance is the distance you travel during the reaction time, during the time it takes you to actually put your foot on the brake. So in that time between noticing the traffic light's gone red and putting your foot on the brake, that's called the reaction time. So let's look at a couple of examples of that. So pause the video to read this question. Press play once you've read it. So you should have now read this question. So let's do it together. Let's follow the Descus method. So let's start by writing down our data. So what do we know? Say your answer to the video now. So you should have said that we know the speed and we know the thinking distance. So we know that the distance is 13 meters. And we know the speed is 20 meters per second. We need to find the reaction time. So let's write down our equation. So I'm going to write the equation using the vector quantities. So displacement equals velocity times time. So the displacement is 13, the velocity is 20, and the time is what we're trying to work out. So therefore time will be 13 over 20. 13 over 20 is 0.65 seconds. And that sounds about right. That is between 0.2 and 0.9. So again, just to explain what I did, I wrote down the data, then the equation, then I substituted and did my calculation, and I didn't forget to put units at the end. You're going to try an example now. Pause the video and try this question completely by yourself. Press play once you've done it. You should have now done this question fully by yourself. I'm now going to go through it. Please mark what you've done as I go through it. So let's write down what we know. So we know the velocity is 12.8 meters per second, and we know the reaction time is 0.52 seconds. the equation, displacement is velocity times time. So the displacement will be 12.8 times 0.52. 12.8 times 0.52. You're always allowed to use a calculator in physics, and that gives an answer 6.656 meters. Don't get confused, by the way, with this S over here. This S over here is displacement, which is similar to distance. And this V over here is velocity. And the T is time. It's just the equation that we looked at earlier. Now let's think about braking distance. So braking distance is the distance which you travel once you hit the brakes until you stop. Now, there isn't an equation for this, but there is something for us to think about, which is what are the factors which will make your braking distance bigger? And what we're actually going to think about is both the braking distance and the thinking distance. So what are the factors that are going to increase your thinking distance, and what are the factors that are going to increase your braking distance? So let's think about this. Thinking distance depends on reaction time. So how fast you can react to the problem in front of you. So the kind of things that are going to affect your thinking distance are the kind of things that are going to slow you down. So the kind of things that might slow you down are alcohol, drugs, tiredness, or distractions like mobile phones or other people in the car. So those things are going to distract you. So they're going to affect your reaction time. They're going to increase your reaction time, and therefore those are going to increase your thinking distance. So alcohol, drugs, tiredness, and distractions will increase your thinking distance. Also, your speed. So your speed doesn't affect your reaction time, but in your reaction time, if you're traveling faster, you will cover a bigger distance in that time. So also speed. So 1, 2, 3, 4, 5 different things that increase your thinking distance. Things that can increase your braking distance are all the things that once you press the brakes will make that distance bigger. So this is all going to be stuff to do with the actual quality of the brakes, of the road, of the car. The kind of things that might increase your braking distance are if your tires are worn down. So if they're old tires that are too smooth, or if your brakes are faulty or worn, so if your brakes are not very good, or if the roads are wet or icy. All of those things will increase your braking distance. And then again, your speed will also affect your braking distance. So the only one that will increase your braking distance and your thinking distance is speed. Otherwise, everything that increases your thinking distance are things to do with you, things to do with your reaction time. And all the things that increase your braking distance are things to do with the car, with the road, with the weather conditions. So you need to know which factors will affect your braking distance and which will affect your thinking distance. And then remember, stopping distance is the sum of the two. So your braking distance plus your thinking distance is your stopping distance. So let's try some examples based on this. Pause the video, write down your answers to this question, press play once you've done it. You should have now written down your answers to this question. This question is all about thinking distance. So thinking distance is all about your reaction time. So what are the kind of things that might slow your reaction time down? Alcohol, drugs, tiredness, distractions, and also speed. Any of those would be correct. If you've written anything to do with the roads or the tires or the brakes, that's wrong. Those are things that affect the braking distance, not the thinking distance. Mark your work. Let's move on. Pause the video and try this question. Press play once you've done it. You should have now done this question. So how will each of these changes affect braking distance? So a slower speed, that will decrease your braking distance. So if you're moving slower, that braking distance is going to be smaller. You're going to be able to stop in a shorter distance. Icy roads, well, your car's going to slide. There's not going to be much friction. So that's going to increase your braking distance. Drinking alcohol, well, drinking alcohol is going to affect your thinking distance, not your braking distance. Remember, things to do with your reaction time, that affects your thinking distance. Things to do with the car with the road, that affects your braking distance. Speed affects both. Pause the video to do this question, press play once you've done it. You should have now done this question, and the definition of stopping distance is your thinking distance plus your braking distance. That is the definition of stopping distance. That is what you should have written down. Please mark and correct it. Press play once you're ready. So you should have now marked and corrected this example. So we're now going to try and link what we've done to the idea of energy. So when you're slowing down, there is a transfer of energy. What energy does the car have when it's moving? Say your answer to the video now. So you should have said, if you remember the energy topic, kinetic energy. So the car has kinetic energy when it's moving. Where does all that kinetic energy go as the car slows down and eventually stops? What store of energy does all that kinetic energy go to? Say your answer to the video now. So all of that kinetic energy actually transfers to the thermal energy of the brakes, of the surroundings, the car, so of the brakes and of the surrounding air. So that's what happens when a car slows down. The kinetic energy, which is the energy related to the car's movement, the car's motion, transfers to the thermal energy of the brakes and of the surrounding air. And what that actually means is, if one was to brake too quickly, that energy would be transferred too quickly and the brakes could overheat. So if you brake too quickly, the brakes can overheat. And also, the car could skid, you could lose control of the car. So let's try some questions based on this. Pause the video, have a go at this. Press play once you're ready. So you should have had a go at this question now. So to do this, you need to know what type of energy is stored in petrol. So the type of energy stored in petrol is chemical energy. And then as the car accelerates, it's speeding up. So the type of energy which is increased is the kinetic energy. So when a petrol car accelerates, the chemical energy in the petrol transfers to the kinetic energy, which is the motion of the car. Now let's think about the opposite. What if a car were to brake? What's the energy transfer this time? Pause the video to write down your answer. Press play once you're ready. So you should have now answered this question. So when a car brakes, it has kinetic energy because it's moving. And as we said earlier, all that kinetic energy will transfer to the thermal energy of the brakes and of the surroundings. If you're ever not sure where energy has gone, usually it's thermal energy. So usually at the end of most energy transfers, there is a thermal energy store. See if you can remember how to do this one. Pause the video, have a go, press play once you're ready. So you should have now had a go at this. So this uses that equation that we mentioned earlier in this video, which is work equals force times displacement. So work equals force times displacement. So to do this example, we're going to do discus. If you couldn't remember the equation, now that I've written it, pause the video and have another go. So you should have now had a go at this question if you hadn't earlier. So let's go through it. So let's start with the data. So the force, it says 2.5 kilonewtons. What should I therefore write down over here? Say your answer to the video now. So over here, I should be writing down 2,500 newtons. I should be turning the kilo into newtons. So kilo means 1,000, 2.5 times 1,000 equals 2,500. And we know that the displacement is 58 meters. So I write down the equation, work done equals force times distance. So the work done is 2,500 times 58. You can always use a calculator in physics. So 2,500 times 58 is 145,000. And don't forget units. What are the units for work? Say your answer to the video now. You should have said joules, because work is energy transfer, 145,000 joules. And linking this to forces, if you remember Newton's second law, resultant forces cause acceleration. So if you press the brakes with a greater force, you're going to slow down over a shorter distance. So a greater force, so a greater braking force means a greater deceleration. You're going to slow down faster. And that can mean that you have a much shorter stopping distance, which could be very important if you want to avoid an accident. So if you suddenly see a child run out into the road, you want to be able to stop very, very quickly. But that is dangerous for the driver and the car, because there are two bad effects, which is one, brakes can overheat when that happens. And also if you press the brake too hard, the car can also skid. So you could lose control of the car and the car could skid. You might have to do it because you might have to stop suddenly because there's a car or there's a person who's just run out into the road, but there are dangers to doing that. So please pause the video to try this question. Press play once you've done it. So you should have now done this example. So the two dangers of a very large braking force are losing control of the car or skidding. And the other danger is the brakes overheating, which can damage the car, can damage the brakes. Please mark your work, pause the video while you do that, press play once you're ready to move on. So you should have now marked this example. So we're now going to do some independent practice. Pause the video to do these questions, press play once you've done them. You should have now done these questions. Pause the video to mark those questions, press play once you've marked them. You should have now marked and corrected those questions. Pause the video to do these questions, press play once you've done them. You should have now done these questions. Pause the video to mark and correct those questions, press play once you've done that. You should have now marked and corrected those questions. Pause the video to do these questions, press play once you've done them. You should have now done these questions. Pause the video to mark and correct those questions. Press play once you've done that. You should have now marked and corrected those questions. Pause the video to do this question. Press play once you've done it. You should have now done this question. Pause the video to mark that question. Press play once you've marked it. You should have now marked that question. Pause the video to do these last two questions. Press play once you've done them. You should have now done these last two questions. Now, in terms of marking them, there is one little thing which I need to do. So I need to do the answers to question 15. So the one with the biggest speed is this one, because that's the one with the biggest stopping distance. Then the other two have the same speeds, but you'll notice that in one of them, the driver's wide awake, and in the other one, the driver's very tired. So in the one where the driver's very tired, that will be the big thinking distance. One where the driver's wide awake, that will be the one without much thinking distance. So please mark your answers to question 15 and 16. Pause the video while you do that. Press play once you've done that. You should have now marked these questions. So in this video, we've learned what stopping distance is. It's the sum of thinking distance and braking distance, where thinking distance is the distance that you travel during your reaction time, and braking distance is the distance that you travel from the moment that you press the brakes until you stop. I hope this video was useful. Please like and subscribe for more videos on GCSE physics.